Hello everyone, I welcome you all in this lecture. So in this lecture, we are going to talk about how to connect the pilot stick with the MATLAB and Simulink, and then whatever the data, for example position and attitude we are getting, how to visualize this data or how to visualize the complete aircraft in a flight gear. So let's say we have a aircraft here. So in the MATLAB and Simulink, what you can do, you can actually model the dynamics. For example, how the aerodynamic forces is acting, propulsion forces acting, gravitational forces acting, using F equal to ma and m equal to I omega dot. So using force and moment and also position and attitude, everything you can model, you can visualize in a MATLAB and Simulink. But how to visualize the complete aircraft, that we can do in the FlightGear. So in this lecture, we will cover how to connect the pilot stick. That means when the pilot will give the command inside from the inside of a cockpit, then these actuators will move and aircraft will respond, and the response you can visualize in the FlightGear. So seeing the graph in a MATLAB, it is important, but at the same time, if you visualize the aircraft in a FlightGear, then it is good to understand. So let's get started.
So hello everyone, now we are in the screen recording mode. So first we will see how to connect the pilot joystick, that means basically pilot joystick test. Okay, so you can see this block pilot joystick is stick. Okay, so here you have an analog buttons and point of view. Okay, so here you have a 6 signal, right? So here first I have used as aileron, and then second elevator, and this is a throttle, and this is a rudder. Okay, from where you can get the block? By directly typing the pilot here. Okay, or this way, or you can go to the what is written here, aerospace block set animation and animation support utilities. Okay, yes, see animation and support utilities. Okay, animation and support utilities. So you can drag this. Okay, so you can use this also, roll pitch ER throttle, or you can use in this you have a more option. So I am using this. Okay, so basically you can connect this stick, okay, directly to the USB port of a computer. Okay, like this. So basically, if you are a pilot, then what you will do, what you want actually, you want like this, right? If I deflect stick in this way, aircraft has to left roll, this right roll, this down, nose down, this is nose up, this is right, yeah, this is left, yeah, using rudder, right? Okay, so this you can configure as a aileron, this elevator, this rudder, and the fourth one, this is a throttle. 0 minimum or ideal position, 1 is a max position. Okay, all right, and you can see different button is also there. Okay, you can use depending upon your requirement. For example, if you click this, okay, so if you press this button, okay, if I run the simulation first, okay, you just press this button. Okay, see, this is a 0, right? If you press this button, the value will go 2. Again, if you release, it will come back to 0. Okay, depending on the requirement. Now this 6 signal, I mean to say, when you, for example, like when you, this is a 0 neutral position, and when you do like this, there will be -1. Okay, and when you do this, there will be +1. Okay, so like that you can check for the or other signal, and when you check this throttle, you will be having a 0 to 1. Okay, 1 second. Okay, if you want to check what was the third one, right? Third one I can correct this. Okay, okay, so if you do this, it will be 1 maximum difference, and this is 0. Okay, this is 0, this is 1. Okay, so like that you can, okay,
This is all about the
how the signal is coming from this block. Okay, you can delete this, and this dead zone I have put is starting from minus 0.05 to 0 plus 0.05. That means accidentally if you deflect in this stick now, so aircraft will not respond at all. Okay, okay, now you can see here. So I this minus 1 and plus 1 I map with the aileron. That means when there is a minus 1, that means this position I will be having minus 35 degree. Okay, and I have to convert it into radian to send you the final aircraft dynamics. Okay, I will send you tell you the later. Okay, and this correspond to the plus 35, right? Similarly, for a rudder, plus 30 minus 30, and throttle 0 to 1, and elevator I have used some mapping function. For example, some function. That means why I have used this, because see this is a non-linear one, right? You can use linear fit also depending upon your choice. Okay, see here the downward elevator and upward elevator are not same. That is why you have used this. I am using this, and for the rest I am not using. Okay, because left and for this side aileron, down aileron, up aileron, both are same. Okay, right rudder, left rudder, both are same. Okay, so that means if you have a this kind of scenario, like for example elevator, so you can use mapping function where the downward and upward elevator is not same. And here I have used -1 because I am considering down as a positive elevator deflection and up as a negative as per as the standard sign convention. Okay, why downward elevator deflection is different than compared to the up? Because when you deflect down, the total angle of attack will be this deflected angle plus whatever the angle of attack aircraft is flying. So there is a chance that you will stall the aircraft. Okay, elevator get stalled because the angle will be this angle plus angle of attack that can go beyond the stall. That is why you have a little less authority, little less authority in downward than compared to the upward. Okay, so basically this four signal I have considered as elevator, aileron, rudder and throttle. Okay, so this we will connect to the aircraft dynamics. Okay, now we will see how to connect this into the aircraft dynamics. So now we will connect the pilot stick to the aircraft dynamics, and then the data which we will get from the aircraft for running the simulation, that data we will send to the flight gear, and then we will visualize the aircraft, okay, in a flight gear. So in order to run the simulation, we have to finalize the initial values, that means trim flight condition. So here SSLF means steady state level flight. So this is the trim condition for a F-18 aircraft. The velocity is 70, angle of attack is 17 degree, and from this you can calculate UVW and PQR. You can set to 0, phi you can set to 0, theta equal to alpha, and psi you can set to 0 north direction, and altitude you can set to 1000 feet. Delta T you can set to 0.54, elevator deflection -3 degree, delta is 0, delta R is 0. Okay, and then I will tell you later that we need actually longitude and latitude information in order to send the data. I mean to say, in order to visualize the aircraft in a flight gear. And for running the simulation, we need in the Cartesian coordinate. So what I did, I defined the latitude and longitude for a San Francisco, and I used this WGS 84 ellipsoid model. So basically this is a world geodetic system 1984, that is why you have it is written 84 here. Okay, so you will send the latitude, longitude and h in this model, and you will get the Cartesian coordinate x, y and z. Okay, so we will use this for running the simulation. Okay, and then again we will convert this x, y, z into the longitude, latitude and latitude. Okay, so this is a Simulink model. Okay, so before this we will run this file. Okay, so we have run this file, saved in the work exposed. This will be utilized by the Simulink model. in order to run the simulation. So this is a Simulink model. So this about this already I explained to you. Okay, and this pilot input will be going to this actuator part. Okay, so here you might have heard this word fly-by-wire system. That means whatever the pilot is giving or giving the command, it is not directly going to the actuators. That means it is going first to the computer, and computer will decide whether we have to we have to accept the command or reject the command, and based on the pilot command it will send to the signal to the actuators. For example, hydraulic system, aileron, elevator, and another and rudder to deflect the required deflections. Okay, but here what I am doing, I am directly connect to the pilot to the input pilot input to the aircraft dynamics via actuator. Here you will see position limit, rate limit, and actuator dynamics. So position, we all know that the control surface has a certain position to deflect. It cannot deflect 200 degree, right? So it has a limit. For example, aileron can deflect plus minus 35, elevator for example plus minus 25 to plus 10, and rudder plus minus 30 degree. Throttle you can move from 0 to 1. Okay, so like that you have to define the position limit. Okay, for example, uh, to be safe side, I have taken as a 10 degree plus positive aileron and 10 minus 15 degree, sorry, 10 degree positive deflection of elevator and minus 15 degree negative. Okay, and aileron is plus minus 35. Okay, and rudder is plus minus 30. Okay, so these are the position limit I have taken, and rate limit. For example, I have taken 4 degree per second. For actual F-18 model, the rate is actually 40 degree per second for the elevator, but to be safe side, I mean to say, I do not want to put those rate, otherwise it will become too sensitive. Okay, because you are not using as of now fly-by-wire system. Okay, so I have little bit reduced the rate. I mean to say, I have divided by the 10 and I have kept it's a 4 degree per second. Okay, similarly divided by 10 here also, and here divided by 10 also. Okay, and this is a second order actuator dynamics. So the reference I will put where I have taken. So basically this is actuator model for F-18. Okay, and for throttle I have used a first order transfer function. Okay, so after passing this actuator model, then you have to connect this to the aircraft dynamics, and this aircraft dynamics part already I explained to you. You can go back to my previous lecture in the system dynamics and control using MATLAB and Simulink course. You will have all necessary information, detailed lecture, and also code available. Okay, you can download that code and you can utilize for your simulation. Okay, and here we need actually density part, because we are going to fly at a different altitude. So I have used the atmospheric model. In atmospheric model I have used the ISA, international standard atmospheric model. Okay, where you will input the altitude, you will get the temperature, speed of sound, pressure, and density. Okay, here you can see the wind model. Also I have considered horizontal wind model, one corner model, and wind shear model. But as of in today class we are not going to use this. In a later class we can make a detailed lecture on this model, how we can utilize this model, okay, in our flight simulation. All right, so once this part is done, you have to run this simulation, then you have to integrate here. Okay, when you run the simulation, then this data will go to this integrator block, because these are the derivative. In the terms of derivative, the question is written, then integration you have to do, and then finally you get the result. This part also I explained to you in the previous lectures. Okay, and then finally the most important part is this FlightGear part. Okay, so this FlightGear part is a most important part here in this lecture. Okay, so here what you can do, you can send the data to the FlightGear and you can visualize. So the way to send the data is, first we need to convert the XYZ. Here I have taken -1 in order to convert from altitude to Z. Okay, and then using this model, which is written flat earth to LLA. Okay, so type here flat. That means you can go to the aerospace block, set utilities axis transformation, you can get this model. Okay, or by typing here directly you can get. Okay, then the longitude and latitude information will be available here, and we know that altitude, phi, theta, psi also, roll angle, pitch angle, and yaw angle. And then you can, these value you can send to this block, okay, and connected to this block we have used net FDM, okay. So basically you have a two option. You can use this block flight gear pre-configured. If you type here flight gear, okay, so you can go to the aerospace block set animation and flight, aerospace block set animation, okay. So you can take a this part, this block you can drag to this block, okay. You can drag to, because you have to send the data, okay. You have to generate the batch file also. You can drag all the necessary blocks which I have taken here, okay. These okay, this okay. So this I am using, this I am not using, because you have a more choice here. Why? Because you can see, you can send the position, velocity, control surface position, engine, fuel inputs, landing gear, environment input also, okay. So here you have a more option, but here you have only limited option. Only you can send, only you can set longitude, latitude, altitude, and this angle phi, theta, psi, okay. All right. So here you can send only longitude, latitude, and latitude, and aircraft attitude phi, theta, psi. But in this we have a more option. So I am sending this position and attitude with the control inputs also, okay. Elevator, aileron, and rudder, okay. And this net underscore FDM is used to send the data to the flight gear. Flight gear will receive use from this using packet only, okay. And this gen fg run is a very important file. You can see when you click this, you have to enter the model name F-18, airport ID, runway ID, initial altitude, offset distance, offset azimuth, everything. And most importantly, you have to enter the port 5504 port already is here. And then the most one more important part is you have to enter the flight gear base uh, directory and this output file name. The output will be generated if you generate this script. The run fg.bat file will be generated, and when you click this file, the flight gear will open, okay. So the flight gear will open, and now if you run the simulation, then you can actually communicate the flight gear to the Simlink, and Simlink to the flight gear, okay. So now we will open the open. So when you click that, this run fg file will be generated, and if you open this file, the flight gear will open, okay. So now we will run the simulation.
Here I would like to mention one very important point. For the present case, I am considering F-18 model, and the related files I have downloaded and have put in the flight gear folder, and so many other aircraft already there in the flight gear folder. But if you want to design your own UAV aircraft and you want to see the simulation and visualization, what you can do, you can actually design, for example, in a SolidWorks, and the SolidWorks file you can import in the AC3D software, and you can put all the texture and all, and then you can put the AC3D file by by going to the flight gear folders in a model. You can put for example, like a, you can go to the flight gear folder and then data and then aircraft, and then you can put this file into, for example, HL20 folder, or you can create your own folder, okay. And just give the model name in a Simlink model. Hope you have remember I told that key gen fg run, I mean to say generate run script file is there. So you have to click that file, and you have to just below that, what is written here, flight gear geometry model name. You have to enter the just a model name. So actually what, from this what you can do, when you generate the script, then bash file will be generated, and you will see your own UAV flying in a flight gear, okay. So now it's time to run the simulator. So side by side screen I have put. When you open that file, batch file, then flight gear will open, and when you run, hit this run button, okay. So see, this part is, see, now I have to little bit increase the pitch, okay. So how this, you can see how this Aircraft is beautifully flying. Okay, now you can press V, you can see this thing. Okay, now you can take left roll. Okay, perfectly taking left roll, perfect. And then if you want to make a right roll, you can put, see the small movement in the stick I am giving, and how this is responding. Okay, this throttle also you can reduce little bit. Okay, in order to maintain altitude. And now you can see the pitch also. You can, if you put forward, the nose down movement will be there. Okay, perfect. Okay, now we can have a full view. Okay, okay, now we can have a full view. So this is a different type of view. If you press V in the keyboard, you will have a different type of view. This is a chase view without yaw. This is a flyby view. Okay, now you can fly in a flyby view. Okay, so this is a helicopter view. Okay, so that this is a chase view. Okay, see this, how this is responding. See rudder also you can see. Okay, huh, perfect. This is a flyby again. So you can roll the aircraft. Okay, perfectly. Now it is rolling. Okay, perfect. See, this is a cockpit view. Okay, by monitoring this HUD view also you can level the attitude. Okay, for example this. Oh, now it's level, right? Okay, okay, again very sensitive. Okay, be very careful here. Okay, not level, right? Okay, level. All right. Okay, you can reduce a little bit. Okay, you can push nose down movement, pitch down. Okay, okay. So if you reduce the throttle, you can go down. Okay, so this is, the altitude is displayed here. That means 28, around 29,000 feet. We are flying. Okay, so I will give the nose down movement here. Okay. So basically, what is happening? Whatever the computation is going on, you are sending the data longitude, latitude, altitude, and position, phi, theta, psi, and then control surface deflection also. Okay, so real time simulation is running in the MATLAB, and you are actually visualizing in the FlightGear. So that is a beauty of a software like a FlightGear and MATLAB. You actually using both FlightGear and MATLAB, you can actually run the simulation and visualize the same. Okay, so if I reduce the altitude, I'm going down, I have to push down motion. Okay, now you can see the altitude is dropping, right? So I put the throttle. Okay, you can see how this altitude is dropping. Okay, from a different view. This is a flyby view. Okay, you can see inside the cockpit. Actually, you can also monitor. Okay, okay. So basically, with this, you can also visualize the graphs also. So you can see the angle of attack is around 3 to 4 degree. Okay, and at the same time, if you want to see this, okay, what data you want to see? Okay, this is the heading angle you are seeing. Okay, okay, and what is this data is all about? This is a speed data. Okay, you can see how the speed is increased. Okay, so like that you can see all the data in a with the running of a by running the simulation, and at the same time the flight gear also visualization you can do, and at the same time you can data also visualize. Okay, so now see, now let's have some feel. Okay, let's say if you reduce this, for example, if you want to put a nose down motion, for example, let's say I am putting nose down. Okay, by giving this stick, so what do you expect? Speed should increase, right? And at the same time if I pitch up the aircraft, for example, let's say I'm going pitch up, so you will have drop in speed, right? So you can have a feel for this, all the parameters fields you can have it. Okay, so whatever the parameter you want to visualize, you can visualize here. Okay, so at the same time what the response you are getting in the MATLAB with the running aircraft, you can visualize and you can have a better understanding of a theoretical concept. Okay, with this visualization. Okay, wow, beautiful. It's inverted complete. Now if I want to roll back, perfectly, now it is rolling back. Okay. Now the task is to level the wing, right? Now I have leveled the wing. Okay, going. Okay, it's taking time, but no problem. I am not a very much expert, what you can say, pilot, but I will try. Okay, what I am doing. Okay, let let the aircraft allow to drive. Okay, and then slowly you can put the stick up, slowly, see, slowly, perfect. Okay, so this way you can do this. Okay, put that in. Okay, so again I will run the simulation to see that how to visualize the, I mean to say how to see the, I mean how to have experience on a low altitude flight. Okay, you can see this low altitude. Okay, so I will not go much, will not gain much altitude. Okay, I want to fly close to the ground. Then you have a more feeling. Okay, okay. So little stick nose down. Okay, then you will reduce the altitude. Now you are flying close to the ground, right? Now you have a good experience. Okay, okay. You see how good you are flying. Okay, close. Now you pull up the aircraft, right? Like this, you can fly the low altitude flying. You can have experience. Okay. So you can take a turn. Now you can fly above the ocean. Beautiful. And keep trying with this flight. So you are flying above the San Francisco. So you will see the red bridge also. So many times I have seen during the flight. Okay. So thank you for attending this lecture. So all the necessary files, I mean to say the code and all everything, I will put in the Google Drive, and the link I will provide you in the description so that you can access the same. Okay. So if you have any doubt, please contact uh, me. Okay, so this is one of the flight visualization software. The another software we can use the explain. So in the future we will cover the visualization using explain also. Okay, so thank you so much.